Just make those.
All right. Hello, everyone. I think we shall start. Okay. So first, again, I'll suggest you to start to do the homework too, right? As soon as possible, because we have 14 days, and you need to implement your linear model. This means your method, which we were going to discuss today, and also boosting and random forest, all kinds of stuff. Those are it's a bit heavy in programming, so don't wait until the last minute. And what else? And I believe by the end of next week should be, this week should be the due for the course project and the course project courses, right? So please make a decision. If you're still like weighing and balancing about what kind of project you're doing, you can come to talk to me, or you can share with your ideas, especially for exploratory project. I have talked to a few students. I think their idea is really exciting. Okay, so let's continue with linear regression. Right? So in the last lecture, we give the brief introduction about linear models, including definition of linear classifier and linear regression, and also the geometry view of linear classifiers. Right. So we mentioned that if we want to do linear classifier, we're going to compute a function we call it linear classification function, which is linear function. And if this function is positive or non-negative, we're going to predict the label to be positive. Otherwise, we predict label to be negative. Right? So this rule can be nicely viewed as kind of line or hyperplane to separate the instance space into two half spaces. I mean, in general. Right? And of all of this, we're going to talk about detailed. I mean, in this week and next few weeks, we're going to talk about different linear models, namely different learning algorithms. Right? So we start with the linear regression. Right? So at the end of last lecture, we introduced a concrete example to apply linear regression. It's a car mileage prediction problem. Right? So suppose I have collected several cars, right, from whatever car rental places, right? So so for each car, we know the weight of its car, we know the age of the car, and also we have read the mileage, right? So we have collected training data. So the question is that next, when I give you a new car, I tell you how heavy it is, right? And how many years it's already driving. Right? Can you predict the mileage rate? Right? So in case that the car owner just randomly modify the mileage, right, to sell you a much higher price. So it's only worth like $10,000, but it sells you like $20,000. That's a lot of money, right? So we're going to use a linear regression model. So basically, we assume the output is a linear function of the inputs. So in this mileage prediction problem, we have two features, right? So x1 represents the weight, and x2 represents the age. Right? So then we're going to predict the mileage as W0 plus W1 x1 plus W2 x2. Right? So which one is the bias term, and which one are the weights?
W0 is the bias, and the W1 and W2 is the weights.
Yes, Yes. So be acute about the definition, right? So we have two parameters in our linear models. First one is called bias term, and second is called the weight vector. So W0 here is the bias term, and I'll also mention that sometimes we can also fold the bias term into the weight vector. That means we actually augment our input vector with a constant feature 1, right? So this can be viewed as W0 times 1, right? And then the learning is to find out a best possible value of this weight vector. So here the weight vector actually has the bias parameter folded in. So for convenience, we just use one bolded symbol to represent all the three values here, right? Three parameters here. Right? So we want to find the best possible value of this W using the training data. So this is called learning procedure. And then given the values for x1, x2 of a new car, we can use our learned weight vector W to predict the mileage for this new car. Right? This is the whole protocol to conduct the linear regression. So in general, we're gonna assume the inputs are vectors that reside in like d-dimensional space. And here, for simplicity, we assume that you have already done feature augmentation, meaning that okay, x1 is always 1. Okay, I have already inserted every original feature vector a constant feature 1, so that I do not need to explicitly deal with bias and weight vector separately. We just put them together. Does that make sense? So don't confuse that. It's fine. So that means any feature vector x is now consists of a constant feature 1, x2, x3 to xd. So after the feature augmentation, we have like a d-dimensional feature vectors. And we assume that we have collected the set of training data, which are m pairs of input vector and output values, right? x1, y1, x2, y2 to x, m, ym. And then we want to approximate the output y as a linear function of x, right? So it's w1 plus w2 x2 plus blah 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 until wd xd. So w1 is the bias term. So for succinct representation, we can simply represent it as inner product between our weight vector and feature vector. Right? So remember, in this weight vector, we have our bias term folded in. And so that's why in our feature vector, we have some constant feature 1. And then, obviously, this weight vector has the same dimension with the input vector x, so it must be d-dimensional. Okay, this is the basic setting. Any questions so far? So everybody's comfortable, right? Okay. So just give you examples, right? So suppose our original input dimension is just 1 dimension. That means I only have 1 variable, right? So my predictor can be written as a linear function in a 1-dimensional space in xy plane, right? So we're gonna learn these blue points are the training set. We're gonna learn a line which is as close as possible to these training data points, right? And then when you are presented with any new test feature, say here, right? So we can find out the value, the y value in this line as our predictions. Some geometry view of our linear regression model. And we can further extend it to 2-dimensional inputs, right? So if our original input vectors are 2-dimensional, and then when we learn a predictor, we actually learn a plane in a 3-dimensional, right? So remember, our linear regression function itself is y equals to w1 plus w2 plus x multiplied with x2. It's actually a line in a 2-dimensional space. If we have 2 input variables, this is actually a plane in a 3-dimensional space. So suppose those red points are your training data. You're actually trying to move such kind of plane, right? You can move it, you can rotate it, whatever. You want to find out such a plane that are close to this training points, right? So of course you cannot guarantee that all the points must stay exactly on this plane. That should be close enough. That's intuitively how we conduct the training, right? Then the problem is that how do we know which weight vector is best for a training set, right? I mean, from geometric point of view, like how do I move this line or rotate this line such that they are close to the training set, or move this plane such that they can close to this training set, right? So how can we measure that, right? We need to come up with some mathematical definition to measure the goodness of the weight vector to fit the training data, right? How can we do that? The idea is that we can look at one particular example, right? So for an arbitrary weight W, right? How can we measure whether this weight is good or not? We can look at, if I use this weight to make prediction, how much difference my prediction is from the ground truth, right? So of course we need to take the absolute value, right? Because it's bigger than the ground truth or less than the ground truth. In general, it doesn't make that much difference. So then we can naturally define a cost or the penalty that I make a mistake to be simply the absolute difference between the ground truth and their prediction. So obviously, the closer your prediction to the ground truth, the smaller cost you make, right? Or the smaller penalty you incur, right? And then we have some kind of metric to measure the goodness of your particular weight on one example, right? How about the goodness for weight for a set of examples, right? For like 1,000 examples, 2,000 examples. How can we define that?
Or the sum of errors or something?
What?
Probably the sum of the errors?
Some of these absolute values? Yeah, that's a great idea. Any other idea? Any other suggestion? Okay, so honestly, we can directly do the summation of the cost over each training example in the whole training set. That's totally doable. And actually, such kind of cost function has many nice properties. But it might not be that convenient in practice to just use absolute value. And we will see it when we try to develop our learning algorithm under another objective. So what is the most common use objective? I mean, most common objective does not mean the best. It just means most common because it's very convenient. So the most common used objective or the cost function defined on the training set that is used to measure. So this algorithm is guaranteed to converge to the minimum if R is small enough. Why? I don't want you to give a rigorous proof. That's the requirement for the optimization course, but intuitively, why? Any guess?
Because at the worst situation, you will reach to local minimum of the diagram. It's the worst situation. If the diagram has multiple minimum or maximum, we will reach to the local one.
Yeah, you're right. But the issue is that why do do you think it will reach some local minimum and stuck there?
Even you have a significant increase for the weight pattern changing.
I think your explanation is kind of closer to what I want to mention, right? But any other comments?
If you want to pass through local minimum in the direction of gradient will channel.
Yes, yeah, it's kind of close, but you have some. Oh, okay. Yeah, let me put it straightforward. Okay, so consider we're keep decreasing our function, right? And we ensure that the learning rate is small enough every time I'm going to decrease the function, right? So you can imagine when it get closer and closer to some minimum or local minimum, as you just mentioned, what's the change of the gradient vector?
It gets smaller.
Yeah, the gradient is closing to zero, right? The gradient eventually, I mean, in the ideal case, when you arrive at the local minimum or global minimum, whatever, the gradient will be zero. Right? So that means when you get closer and closer to some minimum, your gradient, the skew of the gradient elements are closing and closing to zero. That means every update, WT plus 1, will get less and less significant. Right? And when you reach, will get closer enough to the local minimum, very probably that it won't get updated because of some numerical accuracy issue. Right? This increment and this decrement is too small, so when you update, there's nothing to update. Okay. And for this particular objective function, I mean our square loss, the local minimum is the same as the global minimum. The reason is our objective function is convex function. So if you still have an impression about our home of zero, you are required to show that some functions are convex. As long as the function is convex, any local minimum is the global minimum. Okay? Any questions so far about this gradient descent framework? I believe that, I mean, up to now you are able to implement your own least mean square approach. Okay, so now let us look at some potential issue of the gradient descent. Right? So something in practice we do not like very much. So see that in every step, right, to perform one update, we need to compute the exact gradient. Right? To compute the exact gradient, we need to go through the entire training set, right? Because we need to compute the error using the current model, make a prediction, and then do the weighted summation of all the errors to get the true gradient, right? So this is okay for a relatively small set of training examples, but nowadays machine learning, the skill of machine learning is really big, right? So what if like my training data contains like 1 billion examples, right? I don't want like every update I have to go through 1 billion examples. That's too costly, right? So what if I even don't have a powerful computer, I don't have enough memory to store all the data set. I even cannot do that. So the gradient descent, I mean the standard gradient descent framework is not favorable to deal with large data set, large training, because the weight factor is not updated until all training errors, I mean all errors are calculated. The error of each training example is calculated. Because this is really inefficient, right? So we want to conduct much more quick updates and much more instant update. How can we do that? So from the computation formula, right, to calculate the gradient. So someone may ask, right, it's quite mature, quite intuitive, right? So why should we go through all the training examples and do the summation to compute gradient and update? So why not I just look at one example, I just compute this part, then use that to approximate the gradient and do the update. So this is called stochastic gradient descent. It's pretty straightforward from the original computation of the gradient descent. People say, okay, I'm kind of reluctant to sum over all the training examples to get one update, right? So okay, I'm gonna like disposing of this summation. I just look at one example. Okay, I compute the error multiplied with the corresponding feature. I got kind of like approximation to the gradient. Then I do the update. That's it. So again, imagine if we update our weight vector like this, it will be much more efficient, right? So suppose you have 1 million training examples. If you do things like this, you go through the entire data set once, how many times you have updated your model? 1 million times, right? And if you use standard gradient descent, just update once. Just update once. So that's the key idea of the stochastic gradient descent. So it's gonna repeat for each particular training example. Pretend that the entire training set is just represented by this single example. Then we use a single example to calculate the gradient and update the model. That's the idea of stochastic gradient descent. So obviously it contrasts with the batch gradient descent. So the standard gradient descent is also called batch gradient descent, which makes one update to the weight vector for every pass over the entire gradient descent. So now let's look at how can we conduct the stochastic gradient descent, right? So again, the very first step, we need to initialize our weight vector, W0, whatever. And then we go through many iterations as well. But then in each iteration, we'll look at those training examples one by one. Suppose the current example is xi and yi. I'm going to calculate the stochastic gradient solely based on this xi and yi. We simply do the subtract. We simply do the yi subtracted by w transpose xi times xij. Remember, this is one summand in the standard gradient computation, right? So this is a minor sign, and because we do gradient descent, so we subtracted some minor stuff. So now it becomes positive. Right? So then we got updated for one gradient element, right? We do it like for d times, we update every element in the gradient vector, in the weight vector. So we finish one update. After we have accessed one training example, right? And then we do it again for the next example, and third example, fourth example, until we go through the entire training example. So you can see one iteration actually have updated the model for many times. So here is the key difference with the batch gradient descent, where you go through all the training examples is to just compute one exact gradient, then do one update. Right? Stochastic gradient descent, okay, just look at one example, do some update, and look at another example, do some update. So this update rule is also called Virchow-Hopf rule in the neural network literature. So right now, not too many people mention this. People just will it as a stochastic gradient descent. So because this algorithm framework updates the model immediately upon looking at one example. So this algorithm is also called online algorithm, because you do it. You can imagine you stream your training data set, right, one by one, and I receive one example, I update the model once. I receive next example, I again update the model, right? So it's also called online algorithms. So when the training set is very large, people usually choose stochastic gradient descent. The reason is just because it's simple and fast. So you can imagine suppose you have 1 billion training examples, right? And if I choose to use the stochastic gradient descent, probably even before you go through the entire data set, you have obtained a model which is fancy and good to use. Probably when you have saying like 1 million examples, now the model has been updated to a very good stage, and it's good to give you a good accuracy. It is good to give you accuracy, enough accurate results. But if you choose to use the standard batch gradient set, well, going through all the 1 billion examples once, you only get one update. So you can imagine, okay, it's still far from sufficient, right? At least I have to run my standard gradient descent for 10 iterations, right? It just goes through once. Right? It's much, much costly. Also, the computation is much cheaper. You can even use your cell phone to do that. Because every time it only needs to deal with one example. So any questions so far regarding the algorithmic framework of stochastic gradient descent?
Do people ever pick more than one training example at once, like 1% or something?
Yeah, that's a very good question. Yeah, so people usually won't just take one example. People usually take mini batch. We call it mini batch.
Mini batch.
Yeah, mini batch, like 100 examples or even 500 examples, and then compute the stochastic gradient.
So for the training example, is randomly selected, or we just go from I equals 0 to how many examples there is?
So in practice, people usually random shuffle the training examples, and then do it one by one. You can view it as random selection. So basically, they're statistically equivalent.
Okay, and then do you put that with replacement or not?
Both are fine.
Is it still guaranteed to reach the minimum?
Yeah, that's a very good question. So, yes, it guarantees. Someone asked, okay, what's the price? Right? It's so fast, but what's the price? The price is that every update is wrong. Because the gradients is wrong. Right? The full gradient, the accurate gradients is summation over all the weighted errors, right? You just do one, it's definitely wrong, right? Probably this direction of full gradient, right? Your stochastic gradient will be like this. But the nice thing is that as long as your learning rate are chosen to be appropriately, there is some fancy and nice theorem to give you the guarantee that with probability 1, your stochastic gradient descent will converge to some local minimum. So you can imagine when you run the stochastic gradient descent, you're like a drunk driver. You haven't drank a lot of wine, right? You don't know where exact direction to the home. The home is some local minimum, right? But what I do, I just random drive north, random drive northeast, random drive south, random drive whatever, right? As long as every time when I drive for a sufficient small distance, eventually I'm gonna arrive at my home. As long as I won't, hate too much, right? My car won't stuck on the road. Eventually I'll gonna arrive at my home.
Okay, so for this algorithm, it updates the weight for every training sample, but I think you still need to go through all the training samples. So I don't think that's like time saving.
No, it's not requires you to go through every training example.
Like on the subset, for example.
As like I just mentioned, right? So suppose you have a huge training set, like 1 billion training set. So it is probably that after you pass through like 1 million examples, you have already arrived at some local minimum. It is possible. So it sounds like a little weird, but it is possible.
So you're saying that it can like reach to the optimal solution. Maybe you don't need before you go through all the samples.
Yes.
Okay.
And also even you have to go through all the training examples. It usually can give you a very good model much quicker than you use gradient descent. Why? Because you use gradient descent, you go through the entire training set, you have only got like one iteration, one update, right? So, but in the same amount of time, you have updated the model many times. Suppose you run your gradient descent, you have like to go through the training set for 100 times to get fancy model. But for me, I just need to go pass through my data set 5 times. It's already very good enough. Any other question or concern about the stochastic gradient descent?
So if you went through the entire training set once and updated W every time, would that mean that your T is still 0? Unlike the on line 2.
Oh yeah, you're right. This is notation issue. Yeah.
So T would be like 0 or 1.
Yeah. But anyway, you can put it like this. This is already being updated.
Yeah.
Yeah. But this is a notation issue.
Okay.
I'll fix it later. Any other question?
This algorithm just pass through data just once, or
No. In general, you should pass data like several times. So in stochastic gradient descent, this iteration is really called like epoch. People call it epoch. If you say I'm training my algorithm, I'm training my model with stochastic gradient descent. They say, okay, I trained it like with 10 epochs or 50 epochs. I mean, okay, I'm gonna go through the data set for 50 times. Another question? Okay. Great. So now let me talk about the convergence guarantee about stochastic gradient descent, right? So in general, how do we guarantee your stochastic gradient descent eventually converge, right? So we must ensure that the learning rate R decreased to 0 finally. I mean, if you update your model for infinite number of times, that means your learning rate must approach 0 in the limit. So that means your learning rate is actually decreasing. And at the same time, it cannot be too small. That means the summation of learning rate, if you view it as a series, right? It's the summation of the learning rates. The limit of the summation of the learning rate is infinity. I mean, it diverges. At the same time, it cannot too large. In other words, the sum of the square of learning rates must be converged. So just bring it back to them because this is not the requirement of our class. I just give you a sense, right? So first, if you want to ensure your stochastic gradient descent to converge, the learning rate must be smartly and appropriately scheduled. So first, it cannot be too small. If it is too small, that means okay, it's gonna stop at some middle point. It won't arrive at some local minimum, right? So how can we guarantee that? We require that the summation of the learning rate, when the number of updates tends to infinity, this summation must be infinity as well. That means diverges. But meanwhile, I cannot let my update to be too large. That means the step size, the learning cannot be too large. Like if I'm a drunk driver, every time I just drive for 10 miles and then change the direction, I will never be able to reach my home. So I have to restrict how much I move along with the stochastic gradient descent. So what kind of condition we should obey, right? That is called the square sum converge. Means the summation of the square of the step size or learning rate across all updates must be limited. It's less than infinity. It cannot be infinity. So under these two types of under these two conditions and under some model condition for the objective function, you can show that with probability 1, almost surely your stochastic gradient descent will be arrive some attraction, meaning some local minimum. But attraction does not necessarily mean local minimum. Does it make sense? In general?
Then the summation is for I and I is from 1 to n. It's finite, yes. So how you can get the summation to be infinite?
No, you do not calculate that. You need to ensure that you have some schedule to update your learning rate at every step t, right? So you need to ensure that summation from t equals 1 to infinity. This is less than infinity or infinity. It's two conditions. So the learning rate is also called step size. So this is just like a brief explanation of this, right? Just have some impression on that. Will be more than sufficient. So the learning rate is also called step size, and how to set this learning rate is actually the key of this hot topic in machine learning. So actually, different setting will lead to different convergence rate. So some kind of smart setting will make you arrive at home much earlier than other naive methods. Okay. So a more sophisticated algorithm chooses the step size automatically and converge faster. This is a hot topic in machine learning research. And also choosing a better starting point can also have an impact as well. This is quite intuitive, right? If your starting point is already very close to the local minimum, then you can imagine that after a few steps you have arrived. You have to be close enough, right? Otherwise, if you starting from very far places away, then you might spend more time, more step size. So in general, gradient descent and its stochastic version are very simple. It's really straightforward. But almost all the algorithms we'll learn in this class can be traced back to the gradient descent for different loss functions, different hypothesis spaces. So see that actually, in general, you can summarize the machine learning procedure as like, I'm gonna, according to what kind of models, classifiers I'm interested in, I propose the loss function, or objective function. Then the learning is turned to an optimization problem. I'm gonna use some gradient descent approach to minimize this loss function to find the best parameter. That's it. Okay, any questions so far?
How to adjust batch size if we use the batch SDD? And what's the relationship between step size and the batch size?
Yeah, that's a good question. So the batch size, there's no like theoretical guidance for you to adjust batch size. So why do people introduce batch size? That's because if you just use one example to compute the stochastic gradient, the variance tends to be too large. Because this part is called stochastic gradient descent. Why? Because it depends on the specific training example you use to compute, right? So if you do random shuffling or random sample example to compute this approximate gradient, it's actually stochastic, right? So that's why it's called stochastic. And the larger the variance of the stochastic, the slower you converge to the local minimum. So in practice, people are trying to sample a small batch of examples. Then you calculate the stochastic gradient. The variance will be reduced. That's the idea. But if you collect too many examples to compute the stochastic gradient, then you imagine you have to spend more computational cost. Right? So there's a trade-off here. But in practice, you have to find the best trade-off between the computation cost you can bear and the convenience you want, right? So I can tell you, commonly used batch sizes to me is 100, 200, 500. I won't use 1,000 examples as batch size. What else?
The relationship between step size and batch size.
in general, if the variance of stochastic gradient is small, you can be more ambitious for your to choose the step size. But usually, I mean nowadays, the step size are determined automatically. It is not computed directly out from the size of your batch size. It's actually computed from the gradient. So some kind of momentum-based approaches will take a look at the difference of the gradient between the previous steps and current step, and then adjust the step size. But you know, this kind of metric actually is reflected to the batch size you choose. Right? So the larger the batch size you choose, okay, the gradient, the stochastic gradient sounds a bit more stable than you just use one single example. Then the step size will be adjusted to be more ambitious. Does it make sense?
Kind of along the same lines, would it be feasible to, or could you get any optimization by using knowledge of past gradients and averaging past gradients?
Yeah, that's a lot of, there are a lot of works in optimization domain. They're trying to do this kind of things. This is called like momentum approach, but usually they won't use like the past 100 gradients. They just use the past 1 or 2 gradients. Any other questions?
So I'm just wondering if we can just view machine learning as an optimization problem.
No, I'm not happy to hear that.
So what's the difference between these?
So what is optimization problem? Optimization people are just interested in how do I get some local minimum or local maximum, or whether it is local minimum, not local maximum, or just the station, just the saddle points, right? But this linear is objective. Why do you use this objective? What's the difference using objective 1 and using objective 2? There's a huge difference. And different, and also different justifications.
So you're saying machine learning is about how to find the objective function?
No. Don't view it like that way. You will piss off. You will make machine learning people piss off. Don't summarize. Don't try to summarize machine learning. What is machine learning? Okay. Because it is kind of cross-discipline. It unifies the knowledge from many disciplines, but it has its own philosophy. At first, how do you model data? If you want to build a model, you should address the problem. What's the instance space? What's the hypothesis space? What kind of underlying assumption is that? So the big bunch of the theories, computational learning theory, they are not talking about optimization at all. And also because I'm doing Bayesian machine learning, and usually I often do not use gradient descent. I use other method. It's called Markov-Chain sampling. I don't use any gradient information. Should I be excluded from machine learning? Yeah, of course not. But there's no doubt that optimization is very, very important in machine learning. So that's why a lot of like optimization people claim they are machine learning people as well. Any other questions regarding the algorithm framework we have discussed so far? Okay, so now we have finished the introduction of the linear regression and the learning approach. It's called this mean square method, right? So the goal is to predict a real bad output. That's the task for regression. Right? The output is continuous, using a feature representation of that, and our underlying assumption is to assume this output is a linear function of the inputs. So to construct linear function, we need a weak vector, we need a bias term, right? So of course we can fold the bias term into the weak vector to get a simpler definition, right? A notation. Right? And then how do we conduct learning, right? How can I identify the parameters of these linear functions? We minimize some total cost. In our linear regression problem, we propose a least mean square objective. Square loss, sometimes also referred to square loss, right? We minimize the square loss, so we use gradient descent or the stochastic gradient descent to find the best weak vector. But I want to mention that the square loss function we have discussed so far can directly have an analytical solution. You even do not need to write Python code to optimize it. So I briefly mentioned how to do that because I highly encourage you to try to prove this, how this analytical solution comes from, right? Because in your homework you're required to calculate that and compare this ground truth solution with what you have learned from the gradient descent or stochastic gradient descent. Okay, so basically, if we represent our training data and training output in terms of matrices and vectors, so we can have a more compact and convenient representation, right? So if you can represent X, I mean, all the M training data by some D by M matrix. Right? So you just put each column as one feature vector for each instance, right? So I have X1, X2 to Xm here, so it is in total D by M matrix. And then we can denote all the output values, Y1, Y2 to Ym, by M by one-dimensional vector, right? So column vector 1. Then our least mean square objective function can be written as this. Let us recall what does the matrix multiplication mean, right? So if you do X transpose W, what does it mean? An idea? You can imagine, right? If you do the X transpose, you actually transpose X, right? So now each row will be some input vector. And then you multiply with W. That means you multiply each row in X transpose with this with vector, right? So actually you do the inner product because you multiply a row vector with a column vector, you do the inner product. So actually you're doing a prediction, right? So the first row multiply in X transpose, multiply with W, you get a prediction for the first instance, right? The second row multiply with vector, you do the second prediction, right? So you have like X transpose will have M rows, means that okay, you have M training instances. So after this X transpose W, you get M by 1 predictions, right? And then you subtract it by Y. Y here is the output vector. So actually you got all the training error in one long vector. And then you do the transpose and you do the inner product of this training error itself. It's just a square. It's just a summation of the square error, right? Is everybody comfortable at that? Or do you feel like too abstractive to think it in your mind? I mean, after class you can put a paper in front of the desk and do that, right? It's just a review of the linear algebra. So now we represent the least mean square error, the objective, in terms of matrix and vectors. We have a more compact form of that, right? And then we can take the derivative over the bit vector directly. So remember, we briefly mentioned how to take the gradient with respect to matrices and vectors in the beginning of the semester, right? So if you're unclear, you can retrieve that page slide. Just one slide should be sufficient to do this. Right? So basically, you still use chain rule on that. This is an inner product, right? X, you can view it as one whole vector, right? So like A transpose A, right? If you take gradient, you first take the gradient of A, so you get X transpose W subtracted by Y as A. And then you do the chain rule, right? you calculate the gradient with respect to this vector for W, and then it will be X transpose. Then you set the whole gradient. The gradient then is also vector. Right? You set the gradient to be 0. You solve that equation. You end up with this. Okay, so I will leave it as an exercise for you, and try to make clear like how this form represents is equivalent to the least mean square objective, and how do we do some gradient over W, gradient of this objective with respect to W, and solve the equation, matrix equation, or vector equation, and then you obtain this. Okay, so okay, we still have like 5 minutes. So I want to give a start for our next learning algorithm. It's called perceptron. So perceptron is about learn a linear classifiers rather than a linear regression. We only have one algorithm to learn a linear regression. It's just least mean square. So we're going to introduce what is perceptron algorithm. We'll see it's really straightforward. Sometimes it's called lazy learning algorithm. And it's online. But there's some associated interesting property with the perceptron. So we'll talk about the theorem. It's called perceptron-mistakes bound. You analyze how many mistakes the perceptron will make, and it'll give you the guarantee that as long as your data is linearly separable, this seemingly stupid algorithm will always guarantee to find out separating hyperplan. It's perfect fit to the training set. And also, to improve perception in practice, of course, we have several variants we'll talk about. Just like we talk about extension to the ID3 algorithm when you train decision trees, right? So first word is the perception, right? So we need to briefly refresh our mind about definition of linear classifiers, right? So in our general definition for linear classifiers, our input is assumed to be an n-dimensional vector. Our output label is binary, is either -1 or +1, right? And our linear classifier, which is also called linear threshold units, classifies an example X using the following classification rule, right? We first compute a classification function, which is a simple linear function in the product between the weight vector and the input vector plus a bias term B. Then we take a look at the sign, right? The sign actually determines the label, right? If the classification function is non-negative, we predict the label to be 1. Otherwise, we predict the label to be a -1, right? So here's some like graph representation of linear threshold units. So you can view each specific feature in your input vector as some node, right? And we have some intermediate node, which in a neural network iteration is called neuron. Right? So each input feature connects to the intermediate neuron, and associated with each edge is a weight. So the first feature is associated with weight 1, the second feature associated with weight 2, until the last feature associated with weight 8, and one bias term, which is associated with a constant feature. Okay? And then the rule is that I'm going to multiply the value in each node with the weight on the edges, and then do the summation. And then we pass this summation to the sign function. Sometimes they call it sign gate or whatever, right? And then it's output. So later when we discuss artificial neural nets, you'll say, okay, I can replace it by other things. I can replace sign by TANH or ReLU or whatever. And also this is a geometry view of linear classifiers. So we have a classification hyperplane. Here is a classification boundary, where all the positive examples stay here on this part, and all the negative examples stay on the other side, right? So I think it's we still have like 1 minute to gossip his history of perception, right? So perception was proposed, was invented in 1958. So this is the original paper. It's published in psychology literature. So it's interesting. The early pioneers, of early artificial intelligence, have strong relationship with psychology. So there's some hype, right? When the perception was invented, like people are shocked, and you see some New Yorker article says, okay, Hamming told you about the giant digital computer known as IBM 704 and how it has been taught to play a fairly credible game of chess. We'd like to tell you about an even more remarkable machine, the perception, right? And which, as its name implies, is capable of what amounts to original thoughts. Wow, it's kind of crazy, right? But I can tell you, perception is not about how to like simulate human thinking or whatever. It's just to find a separating hyperplane from binary data sets. That's it. And it's an online algorithm. Each time it just processes one example at a time, and it only updates model when we make mistakes. So also there are several errors exist. Okay, so we're gonna dive into the detailed perception in the next week.